Floriana, thank you very much for the introduction, and Kenichi Soga from UC Berkeley, and Dave, Amanath, Khalid, thanks a lot for having me here. What I'm going to talk about is a water distribution system as part of the Berkeley Center for Smart Infrastructure that Berkeley Civil Engineering is been working on in the past few years or so. The work that I'll show a little bit is on the city-scale multi-infrastructure network resilience and simulators. You can see on the peer report that we worked about a few years ago. So the details are available in that particular report. Are you hearing okay? Yeah. Sorry. We work closely with infrastructure owners and, of course, water infrastructure owners and other infrastructure owners, and really trying to feel how we can make our infrastructure smarter. And this is the network of East Bay Mud. I'm going to talk a little bit more about East Bay Mud because it's part of the San Francisco Bay Area. They have a pipeline rebuild project that's going on in the past 5 years or so. It's really to trying to upgrade their infrastructure, especially pipelines. And there's 4,200 miles of pipelines. As you see, the oldest is 1877. They're rebuilding every 20 to 25 miles per year. It means it's going to take 200 years. So how do we increase the rate? And at the same time, if you look at the expenditure, they have about $1 billion budget every year, and 25% is used for pipeline replacement. So it's a huge thing. If we can do something, that would be a great achievement. If you look at all these are different pipelines, you get lots of data, and then you can do a little bit of statistical analysis, how things are going. And this is one of the data sets that we've been looking at. And of course, machine learning and data analytics is a big topic, so students love to start looking at these data. But the top figure shows that in terms of if your pipeline is a fault zone, and if it's not on fault zone, this is a survival curve in terms of years. So if you look at the horizontal axis of years, up to 100 to 160 years, and how statistically showing that if you're in the fault zone, yes, it doesn't survive, so more likely to fail. But you can look at, there are other features like landslides or traffic load or pressure level, and all these things comes together. How do we work together is something that we're working on. Unfortunately, this particular video didn't work, but at Center, we do a lot of pipeline testing. So you can see that pipeline in terms of compression, tension, bending, also what we call biaxial, bend and then pull. But at the same time, we got acquired split basin test. It's a big soil box from Cornell University that will mimic the fault rupture like what you see on the right. So we've been doing a lot of testing of different types of pipeline and pipeline joint system. 8-inch, you can see the earthquake-resistant ductile island pipe, IPVC, a plastic pipe, 24-inch, again, a bigger one by Kubota, and then the one on the top is US pipe, and then we just finished the 48-inch, so 48-inch is one of the largest that we have done, and this is a US pipe, a ductile island pipe. And the point is that how it performs. So what I'm going to show you a little bit of the video that we've been show the Kubota pipe. And the video doesn't show any sound, so I just have to do it live. There was some background explanation of what's going on. So it is a 4-point bending test. It's pressurized, and then you can see that it's being bended. It's a Kubota joint pipe. And you can see that it's been bending quite a lot. And it keeps on going. No leaks. 22 degrees down. And after 22 degrees, you'll see a sudden break. Nice. So you can see how it well performs, but at the same time, how we can improve. Yeah, they look happy. All the things are all available through the report, ARS website, so if you're interested, please have a look, and maybe that gives you information of how we look at these pipes. Obviously, we do very detailed analysis of the pipe at the joints and see how we can improve the joints. And this is being bent, and then after bent, you pull. And then how the interlocking happens, and then how we can improve the joints. Here's another site. If you live in Berkeley area, you know Claremont Hotel. I'm not sure you stayed, but it's very expensive. But they have a pool next to it, so there's a pool, and there's a Claremont Avenue. And for those looking at LBNL, maybe you're going in that particular route. And then East Bay Mud just replaced the pipeline over there, crossing the Hayward Fault. And if you're drinking water in the Berkeley, that's where the pipe is going through. Water is going through these pipes. At this particular pipe, it's a critical pipe, as you can see, and then you see the background of the two pipes that were being replaced, 36-inch and 22-inch plastic pipe. And then what we did in this particular project was that we installed the fiber optic sensing. We've been working on this technology for 15 years, 20 years, and then trying to see how the market can accept this particular technology. And basically, you put the fiber optics on the crown. Of course, we like to put it on the spring line, but because of the trench, it's very difficult to attach. So you have to compromise, and we put it on the sort of 3 location. So as the pipe bends, you see a tension and compression on the 2 sides. And then what you do is that you can have a temperature sensor as well, the strain sensor. And basically, this particular fiber optics interrogator does is you shoot a light, and every point, a light comes back, and you look at what that particular signature of the light coming back scattering from that point, and that gives us a noise, which is acoustic sound, or strain, or temperature. So you can see that the pipe is laid, fiber optics is laid on top. You see a white line on top of the pipeline, and that's where the fiber optics is aligned. There's some fiber optics embedded in the trench. But the idea is that if you sort of bend it, you'll see on the one side, as you can see from the right bottom figure, sort of a tension in a distributed way, and then compression in a distributed way. And that difference is the bending strain. And if you integrate trace, you can get the lateral deformation. Obviously, the average is the actual strain, so we can also look at how behaving compression and tension. First of all, we'll look at the temperature. So we have a temperature cable attached to the pipe, and then also in the trench. And then actually we do have a temperature of the water from the East Bay Mud. And if you compare the two, they match nicely, as you can see on the left. And the right figure is about where the manhole is and how the outside temperature compares to our data set. And that gives us the feeling that our sensing is going very well. And then you've been monitoring. We did this installation about a year ago, and we can coming back and making readings, and you can see that it gradually developing a tension. So these are the data sets, and then you can see how it's developing with time. But basically, if you look on the left top, you see a tension because the Hayward Fault is moving, splitting, and therefore there's a tension, but also there's a bending part at these sort of this particular 2 locations. So these are the mechanisms that we see from the data sets. This shows the distribution of the strain. So that's a strain all the way along this particular at different location of the pipe. If you integrate that, you get the displacement. So if you look at the displacement, you can look at the actual displacement of the pipe. And let's say you have to integrate, so you have to start from somewhere over the origin, and then from the east side, which is fixed. And as you can see, how things are moving with time, and then eventually it's sort of looking at the red zone, which shows about 7 millimeter movement about a year. So that makes sort of sense for those who were working in this sort of area. Actual extension about 7 to 10 millimeter, and lateral deformation of 2 to 3. Obviously, the pipe is also expanding, thermally expanding and contracting due to the seasonal changes. And that has an effect as well, but in the right order of magnitude that we feel. So we can look at these sort of deformation and understanding. So we're really interested in all the database coming out, and then how we can link with actual movements. This is another one at PG&E and Gilroy. We just install a similar installation across the fault. The point here is that you may do a lot of these simulations, you can see, and this is some of the simulation we do in 3D in terms of soil pipeline interaction and then how it responds to faults, and we do this all the time, and then we try to create a design. But when you go to a site, actually you go to a site and you see this plastic pipeline, but what you see also here is an abandoned pipe. It's always like this, is that it's not the same as what we want to model, and is this abandoned pipe going to support when the fault rupture happens, or is it going to affect in a negative way? We don't know. That's why we want to monitor. So this is what we're doing right now, but the point is that once we bury a pipeline, we're not going to see it for another 100 years. So why don't we put the intelligence right now? It's for future generations. So that's our spirit. This is colleagues of simulation, so I have to go to a little bit of simulations. We have done some work on the hydraulics. So again, this is a fault zone along the Hayward Fault, 7.05. We don't know where the epicenter is, but we created epicenter, and then looking at the ground motion, we hope to work with your colleagues over here to update this type of simulation. But the point is that once you do this simulation, we look at the fragility curve of the pipelines, and then trying to see, okay, what kind of scenario, how much water each customers will get, and that sort of thing. So what we do is that you do earthquake scenarios. Let's say you generate hundreds of earthquakes, and you're expert on these. And then you do in this case, it's a PGV, sort of a map, local PGV maps. And then we're trying to use the fragility curve to find out what the fragility of each pipeline is going to be. And then you use some simulation, again, Monte Carlo simulation of different scenarios, and then see how the water is going through that particular system, and how much each customer is getting, which customer is not getting water, and that sort of thing. So if you're looking at this sort of certain scenarios, that you can see a pipeline for probability over here on the left. So that is the sort of probability if I think the epicenter, it looks very close over here. So if you have a epicenter close around here, you see a more sort of a pipeline damage. At the same time, here is the sort of a water shortage, and in this particular case, because there's a lot of pipelines are broken, and therefore, actually, they're quite a distributed distribution of the water shortage. The important thing is that because once you do a different earthquake motion, there are different location, and then the population, the ground motion, they're all different. And that creates a different probability or failure events of the pipeline, and it's diverse. So for example, this one shows that pipeline number on the horizontal axis, and the shortage radius, how much water people are getting and how much are not getting, to be honest. So if you say 10% of the population is not getting the water. And the point is that this is 7.05 magnitude earthquake. And then depending on the scenario, you may have a sort of almost 50 breaks, or you can have 700 breaks. So it's so variable. And the point over here is also, you can see that as the pipeline failure increases, so each point is earthquake scenarios, and then pipeline failure scenarios. And then once you look at it, you say, okay, at the beginning, maybe if you only have 100 breaks, they're rather isolated, so you just try to fix the isolated one. The water shortage doesn't propagate, it just very localized water shortage. But once you have more pipelines, they start to interact each other, and you have a much larger coverage of water shortage. And that's what you see over here, is that this particular curve is nonlinear. And therefore, the interaction of the water network creates additional effect in terms of shortage. Obviously, a pipeline is important, but then valves are all important as well. So valves are as old as pipelines. Pipelines are easy the damage of the pipelines is easy to detect, because if you don't get water, that's it. But valves, you have to check whether it's working. And then therefore, and sometimes there's 1900 valves made old. It's 100 years old, 120 years old. You don't know where it's working. Sometimes somebody paved on top of it, so you don't know, you know where it is, you don't know where it is. It may be there, or it may be there, I don't know. So there are a lot of interesting issues in terms of sort of a record of the valves, and then how we deal with the valves. But when rupture happens, you have to repair the pipes, and therefore valves are very important. Just looking at this particular one, which is Alameda Island, for those who live in the Bay Area, you know the Alameda Island, and then trying to see what is the sort of a risk of these valves in terms of trying to fix it. So that was another project that we were involved. As you can see, these are different valves. And it's quite nice to see, if you're interested, if you walk around, you see a valve, and then for those working in this area, it's East Bay Mud, but then you see the logo saying the older companies. So everything is inherited, and then you see all these things, but you don't want to see something like this. And the one you see on the bottom is sort of deployed valves already, which is shown in red dots. And then what you can do is that, what are the opportunity to increase the valves? How do you add the valves? And that was the exercise that we've been looking at, is that you have the existing valves, what are the probability? But even with the existing valves, you don't know how many are working. So at the moment, then you have to say, okay, if the 20% is not working, what is the risk? If the earthquake happens, perhaps some of the more valves will not work. What are the risks of that particular condition? And once you do the simulation, actually it's not a very easy simulation, because you look at each valve or combination of the valves, and you can see how the water network is associated. And then if you do a brute force analysis of every valve that you see in the Alameda Island, and you see that each simulation of the water network takes about 1 second, and if you look at all the combination, probably it takes about 100 years to do the simulations. So that leads to more of a data analytics and machine learning side of looking at these problems. So we looked at data analytics, machine learning type of, data analytic type of tools, and then hydraulic network to create when an earthquake what is the sort of risk of how many valves are not working, and what is what we call direct risk, which is the customers, the pipeline were broken, will be direct, but then if the valve is not working, it affects the other neighbors as well, and what we call the indirect risk. So what you see on the bottom right is about failure rates, so how much valve is failed, and then the vertical axis is the direct risk and the indirect risk in terms of certain normalized way. And how many valves you think it's not working on the East Bay Mud area? Oh, wow, that's a lot. It's about 20% perhaps. Yeah, but we don't know. And then some organization check their valves every year or every 2 years. Some organization may just do every 10 years. So again, it's quite an interesting problem, but also creates additional risk. So again, it's a little bit away from the earthquake motion, but I hope that you see a little bit of a link to what you're going to provide and how it links to all these sequence of things that water network colleagues are interested in. This one just shows that, okay, you have existing systems, and then you can see the total risk, which is the vertical axis, and number of installed valves. At the moment, there are 2,000 of them. If you start from scratch, and then you say, let's put the valves in a right position for this pipeline network to remove, that will be this particular lower bound, which is blue. Obviously, as you increase the number of valves, your risk of the system risk goes down. And for those who are looking at the valves, you know n and n-1. But the point here is that you're currently in this situation. So our also thinking was that, how do you start adding the valves so that you can start to go down to reach to this level, and how many additional valves you need to make this particular system more resilient to any pipeline breakage, so you can fix it. Obviously, we're also interested in sort of a digital twinning of the subsurface, so you can see the ground penetration radar and trying to map the infrastructure. As you can see, that water network is the East Bay Mud water network shown on the right, and then the road network is shown on the left, and basically every road has pipelines. And so the network is similar in a sense. What we do in our simulation, we have simulators in a sense of network simulators. So in Bay Area, there are about 15 million people living. There are about 7 million people living, and there are 50 million trips every day. So we do agent-based model of every road moving around, and then cars moving around a day, and then we can say, okay, if the Bay Bridge goes down, what's going to happen to the traffic? And we've been using this for wildfire evacuation and that sort of thing. But the point here is that everything is a network. Pipeline is a network. Gas pipeline is a network. Traffic is a network. And then obviously all these networks are linked together. And that's our interest. So this is my final slide showing that we do earthquake motion. This is where we want help from you. We will look at pipeline damage. Obviously, a pipeline damage, look at the age of the pipe and the material of the pipe. But every pipe is different, so we're looking at how to sort of refine that particular fragility model, and then trying to do water network simulation. But we want to do lots of simulations to understand what if scenarios and all these things. And then looking at the average water shortage or standard, but then looking also to red tag buildings, which our colleague SimCenter is doing. And these tools are all embedded in the SimCenter tools, as well as transportation, and trying to see the link. So the point is that at the moment, what we're looking at with the East Bay Mud and the Water Agency is really to develop a strategic response and recovery plan using this tool. If the red tag building, there are a lot of red tag buildings, there's no need to recover the water at the beginning. We have to make sure that it recovers at certain places that we need. So thank you very much.